Short for numerical Python. It's a Python library used for numerical computing. It's widely used in fields that involve heavy data processing such as data science, engineering, artificial intelligence, and machine learning. Python is currently the most popular language for AI and machine learning for a few good reasons. It's easy to read and write with, it has a massive ecosystem of libraries, and it integrates well with technologies like APIs, databases, and web applications. This makes Python a top choice for building and deploying real-world AI solutions. However, Python is really slow. That's where NumPy comes in. Under the hood, it's written in C, which is magnitudes faster than regular Python code. With AI and machine learning, you're often working with massive datasets and you need to do a lot of number crunching. Plain Python lists, not gonna cut it. NumPy gives us access to NumPy arrays, which are faster than native Python lists. Plus, with NumPy arrays, we can perform vectorized operations. For example, multiply all the elements by 2. With a Python list, multiplying a list by 2 would repeat all the elements twice. NumPy gives you the speed and the specialized tools you need to handle large-scale numerical operations efficiently. So, let's jump right in. Alright, let's get started, everybody. You'll need an IDE to work with. Currently, I'm using PyCharm, but the IDE you use is up to you. We'll need to download NumPy. It's an external library. We can do that by opening up a command prompt or a terminal. If you're using PyCharm like me, you can go to this terminal button in your toolbar, or if you're on Windows, you can hold Alt and F12. For some reason, if those options don't work, you can always do a search for terminal. Terminal. Those are a few different ways to get to your terminal. We're going to type the command pip, pip's our package manager, install NumPy. Enter. And then we just have to give it a little bit of time. Alright, we can close out of this window. After downloading NumPy, we'll have to import it. We do need to import NumPy into our Python file. You can type the following command. Import NumPy. Then for convenience, we can give NumPy a nickname or alias. Import NumPy as NP for short. Now to check the current version, you can type the following. You can print np, that's our nickname for NumPy, dot dunder, meaning double underscore, version, then dunder again. This will print the current version, just to make sure that it's working fine. Currently, my version of NumPy is 2.3.1. Moving on. Normally in Python, to create a sequence of data, you can use a list, you can use a tuple, you can use a set. Let's say that we would like to create a list of numbers. We'll name this list my_list. It will equal some numbers, 1, 2, 3, 4. Then we can print our list. Print my list, and we have the numbers 1 through 4. Let's say that I would like to multiply all of the elements by 2. With the native Python list, if I was to multiply this list by 2, let's say my_list equals my list times 2. This would duplicate all of the elements by 2. 1, 2, 3, 4, 1, 2, 3, 4. A NumPy array is superior to a Python list. It's faster and gives us more operations. Rather than using a Python list, here's how to create a NumPy array. Let's name this array just array. Equals access the NumPy library. Remember, we gave it a nickname of np. np dot call the array function, and then pass in a list. 1, 2, 3, 4. And then we should be able to print it. Print our array. 1, 2, 3, 4. Just to verify that it is a NumPy array, you can print the following. You don't need to, but here's how. Print the type of our array. Our array is a NumPy ND, meaning n-dimensional, array. Then if you would like to multiply all of the elements by 2, all you gotta do is take our array equals array times 2. And that's going to double the elements in your array. Alright everybody, and that is your first lesson using NumPy. We could say something like array equals access the library of NumPy dot call the array function, and then we can pass in one of a few values. A zero-dimensional array, think of it like a single point. I could pass in some value, like a character. This is a zero-dimensional array. And to check that, there's actually an attribute. Let's print access our array, access the attribute of ndim, meaning number of dimensions. The number of dimensions of our array is 0. It's a zero-dimensional array. If we had a few values within a list, let's add a few characters here. I'll just pick the first few characters of the English alphabet. A, B, C. This is now a one-dimensional array, like a single row. Now the number of dimensions that we have is 1. Let's convert this to be a two-dimensional array. I'll enclose our list within another list. And I'll add a few more lists. We'll add a few more letters. D, E, F, and then I'll just do some copying and pasting because I'm lazy. G, H, I. If you were to arrange your lists like this, they would form a sort of two-dimensional matrix. This is a 2D array. Sometimes people refer to it as a matrix. There's rows and columns. If I was to print the number of dimensions, that would be 2. It's a two-dimensional array. Now we're going to go to an even higher dimension, 3 dimensions. We'll enclose our 2D list within another list. And just for readability, I'll put each two-dimensional list on a separate line. Now we'll create a 3D array. We'll take our 2D array, copy it. Do pay attention to the number of brackets. We're not copying the outer set of brackets. Comma separate each 2D list. And then I'll replace some of the letters. I'll fast forward the video. Feel free to pause it if you need more time. Now, this is very important. I ran out of letters in the English alphabet. Each of these lists, they need a consistent number of elements with each other. It has 2 elements. All the others have 3. If I was to run this program, here's what happens. Value error, setting an array element with a sequence. The requested array has an inhomogeneous shape after 2 dimensions. We need a consistent number of elements within each list. This list has 2, all the others have 3. What you could do is add some sort of placeholder. I'll just use a space, but an underscore is another good option. Now this should run fine. Now the number of dimensions for our array is 3. It's a 3-dimensional array. You could go beyond 3 dimensions too. You can go to 4 dimensions, 5 dimensions, but that's going to be outside of the scope of the series. We'll stop at 3 dimensions to try and keep it simple. We have a 3-dimensional array. You can also access the shape using this attribute, the shape attribute. This will return a tuple of integers. It shows you the depth, the number of rows, and the number of columns. We have 3 layers. Think of it like it's a cake, a layered cake. That's the topmost layer, the middle layer, and the bottom layer. Each layer has 3 rows. 1, 2, 3. Each row has 3 columns. 1, 2, 3. If I was to remove one of these layers, the shape of our array is going to change. I'll delete the last layer. The shape of the array, it's still 3-dimensional, but it has 2 layers, 3 rows, 3 columns. If you ever need the shape of an array, you can access the shape attribute. Let's undo the last changes we made.
So I'm a Java developer.
Previously with the Python list, you would access an element like this. I'm going to print access our array, then you would use chain indexing. For example, I need the first layer that would have an index of 0, the first row, also 0, then the first element, the first column, also 0. That would print the character A. This is known as chain indexing. But with NumPy, we have access to something called multi-dimensional indexing. Here's what it looks like. You'll only be using a single set of straight brackets. Then comma separate each index. 0, 0, 0. That would print A. For the next element, that would be B. 0, 0, 1. 2 would be C. If I was to access 3, well, we would have an index error. Index 3 is out of bounds. For the next row, you would need row 1. Row 1, column 0. That gives you D. Row 1, column 1 is E. So let's see what 111 is. That is N. That's layer 0, because with programming we tend to start with 0. This is layer 1, row 1, column 1. So that gives you N. That is multi-dimensional indexing, and it's actually faster than chain indexing. Here's an exercise. We're going to form a 3-letter word using string concatenation. We'll say word equals. Now pick 3 letters. For me, I'll pick A, S, then S again. We'll access these letters via multi-dimensional indexing. For an A, I need layer 0, array, layer 0, row 0, column 0. And then let's print our word. Print word. That gives me A. Then I will add, using string concatenation, array at indices of, let's see, layer 0, layer 1, layer 2, layer 2, row 0, column 0. That would output AS. And then I'll add that again. Array, layer 2, row 0, column 0. And my 3-letter word that I picked is ass. So for your homework, why don't you use string concatenation and post a 3-letter word in the comment section? I might regret saying that. And that is an introduction to multidimensional using NumPy. Let's get into it. We'll need an array to work with. For this demonstration, we'll create a 2D array. Array equals NP, call the array function. Then we'll pass in a 2D list. There will be 4 rows and 4 columns. So within this list, we will have 4 nested lists. We'll have the numbers 1 through 16. That should be enough for this demonstration. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, 14, 15, 16. Just for readability, I'll put each row on a new line. There we go. We have a matrix of data, a 2D array. For array slicing, we'll be using the subscript operator. I'll add this as a comment. We will access our array, use the subscript operator, which is a set of straight brackets. Here we will write a slice expression. There's 3 options. You can list a starting index, an ending index, and a step. Each is separated with a colon, a slice operator. Let's give it a try. Let's say I would like the first row in my 2D array. Here's how I would print that. Within a print statement, I'm going to access our array, use the subscript operator, which is a set of straight brackets. Then we will list where we would like to start. Let's access array at index 0. That's going to return the first row, 1, 2, 3, 4. Array at index 1 would be 5, 6, 7, 8. Remember that with programming, we tend to start collections with an index of 0. So that's why the second row has an index of 1. The second index would be row 3, 9, 10, 11, 12. Index 3 is 13, 14, 15, 16. Then if we access 4, it's out of bounds. You can also use negative indexing. Array at index of -1 would give you the last row, 13, 14, 15, 16. Or -2 would be the second to last row, 9, 10, 11, 12. That is the starting index. At which element would you like to start? You can also select a range. We need both a start and an ending index. Let's select the first three. We'll start at index 0, colon, that's the slice operator, and end at 3. Now the ending index, it's exclusive. So if we need the first three, that would be 0, 1, 2, 3. That will give you indices 0 through 2. Because the ending index is exclusive, we have row 0, 1, 2. Or perhaps I would like the first 3 rows after index 0, or row 0, so to say. Well, we'll start at 1 then, continue to 4. We'll skip index 0 and print the next 3 rows. If you would like to select everything up until the end, you can omit the second number, but you still need that colon. This tells Python select everything up until the end. Now we'll introduce a step. Let's select every second row, starting with the first. Row 0 and row 2. 0, colon, 4. This will select rows 0 through 3. Remember, the ending index is exclusive. Give me every second row. We'll add a colon, and then the step. We're counting by 2s. This will give me row 0 and row 2. 1, 2, 3, 4, 9, 10, 11, 12. If we're selecting all rows, you can omit the start and the end, but you still need those 2 colons. And the reason that you need them is because if we omit the colons, NumPy thinks we're selecting the second index. So with those 2 colons, if we omit the start and the end, we're telling NumPy select all rows. You can also set the step to be negative. This will return all the rows reversed. So we have the bottommost row, 13, 14, 15, 16, at the top, and the rows are in reverse order. I'm actually curious, what if you set this to -2? Oh, that's interesting. I didn't know that. Now the rows are in reverse order, and we're selecting every second row. I actually didn't know that. I was just curious. I was wondering what would happen if I put -2 here. Alright, so that is row selection. Now we'll get into column selection. Now we're going to get into column selection. We can select specific columns. This first column has an index of 0, because with programming, collections tend to have an index of 0 to begin with. This next column would have an index of 1. The third column has an index of 2, and the fourth column has an index of 3. When accessing our 2D array, we'll need 2 indices, for example, 0, 0. The first index is for the row, the second index is for the column. Now, if you would like to select all rows, for the row selection, we're just going to add a colon. Because without it, we're going to have a syntax error. Invalid syntax. For the row selection, we do need something here. We're selecting all rows, then access column 0. That would give me 1, 5, 9, 13. 1, 5, 9, 13. Column 1 would be 2, 6, 10, 14. Column 2 is 3, 7, 11, 15. Column 3 is 4, 8, 12, 16. If I set the index to be -1, that's going to return the last column, 4, 8, 12, 16.
Voice is simply faster, more natural, and more flexible than typing. He said he's voice-pilled, and I can see why. Whisper.
Or the second to last column would be -2. 3, 7, 11, 15. 3, 7, 11, 15. Now we'll select a range. I would like the first 3 columns. This would be column 0, column 1, column 2. We need a start and ending index. We'll start at column 0, so this number is going to be 3, because the ending index is exclusive. This will print the first 3 columns. We have 1, 5, 9, 13, 2, 6, 10, 14, 3, 7, 11, 15. That is the first 3 columns. Now we'll skip the first column, but print all the columns that come after. We'll start at column 1, or index of 1, so to say, continue to 4. So we skip the first column, this one, we're skipping it, and print all the columns that come after. If you would like all columns until the end of your data, you can omit the step, but you still need that colon. That works as well. Now we'll select every second column by setting the step. We'll be given column 0 and column 2. We have 1, 5, 9, 13, and 3, 7, 11, 15. Now I would like every second column, but we'll start at column 1. That would be 2. This gives us 2, 6, 10, 14, and 4, 8, 12, 16. Then you can reverse the order of the columns. Set the step to be -1. We have 4, 8, 12, 16, 3, 7, 11, 15, 2, 6, 10, 14, and 1, 5, 9, 13. If our step was -2, this would be in reverse order, but we're given every second column. 4, 8, 12, 16, 2, 6, 10, 14. Now we're going to combine both row and column selection. We'll need 2 indices. Let's say that we would like the first 2 rows, but only the first 2 columns. We'll start with our row selection. We're starting at row 0 and end at row 2. 0, 2. Then for the column, we need the first 2. 0, 1, stop at 2. 0, 2. That's going to give me the first 2 columns of the first 2 rows. It's kind of like we're selecting a quadrant. This is a 4x4 matrix, and I would like to select these 4 numbers. Now we'll select this quadrant, 3, 4, 7, 8. Take a guess as to what you would have to write. We're selecting the first 2 rows. We can keep the selection the same for the rows, but for the columns, we're starting at, let's see, 0, 1, 2. 2, 4. But since we're selecting all columns till the end, we can omit the second number, but we still need the colon. So we get 3, 4, 7, 8. Now we'll select the last 2 rows, but the first 2 columns. What row are we going to start with? 0, 1, 2. Continue to 4, but since we're continuing to the end, we can omit the ending index. Now I would like the first 2 columns. That would be 0, 2. And that's going to give you this quadrant, 9, 10, 13, 14. Now we need the last 2 rows and the last 2 columns. We'll keep our row selection the same. Start at column, let's see, 0, 1, 2. Continue to 4. But since we're continuing to the end, we can omit the second number. And we should get 11, 12, 15, 16. This quadrant. Alright everybody, that is slicing in NumPy. I can't think of any homework for you to do. Well, it's kind of important. There's a couple different sections to this topic. We'll begin with scalar arithmetic. Scalar, it's a linear algebra term. Really, it just means a single value. We can apply operations with a scalar, a single value, to entire arrays. We covered a little bit of this in the first video in the series. We'll need an array to work with. I will create an array named array, np.array, then just add a few numbers. I'll add the numbers 1, 2, and 3. That's good enough. Then I will print our array. Now here's where scalar arithmetic comes in. We can apply a single value to each element within an array. If I were to take our array plus 1, each value would have 1 added to it. We have 2, 3, 4. Let's subtract 2. We'll just go through all the basic operations. Array minus 2, 1, 2, 3. Subtract 2 from each would be -1, 0, 1. Let's multiply by 3. Array times 3. Array times 3. We get 3, 6, 9. Array divided by 4. Array divided by 4. We get 0.25, 0.5, 0.75. Let's raise each element to the power of 5. The power of operator is 2 asterisks. Raise each element in our array to the power of 5. 1 to the power of 5 is still 1, 2 to the power of 5 is 32, 3 to the power of 5 is 243. That's basic scalar arithmetic. Scalar is a linear algebra term. It just means a single value. Now we'll cover vectorized math functions. A vector is another linear algebra term. A vector is a single dimension, such as a 1D list, whereas a scalar is a single value. Using vectorized math functions, we can apply a function to an entire array without writing a loop. Here's what that might look like. Let's say I would like the square root of each of these numbers within our array. Well, the NumPy library does have some built-in math functions, just like the math module. We'll access the library of NP, which is NumPy, call the square root function, pass in our array. The square root of each element are these values: 1, 1.4 and some change, and 1.7 and some change. We can round each value. Let's change these numbers: 1.01, 2.5, and 3.99. Let's round each number within this array. NP, call the round function, pass in our array. Here are all the numbers rounded. We have 1, 2, 4. To always round down, you can use floor. 1, 2, 3. To always round up, you can use ceil, meaning ceiling. 2, 3, 4. There's different built-in math functions you can apply to entire arrays. You can access them via the NumPy library. There's also built-in constants too, for example, pi, np.pi. That would return pi, 3.14159, blah 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 blah. Basically the first 10 plus digits of pi. Let's go over an exercise with vectorized math functions. Let's change our array to be 1, 2, 3. And let's say that our array is actually radiuses, or radii. I think that's plural for radiuses. I don't know, I'm a coding tutor, not an English teacher. We have an array of radii. Given each radius, we will convert it to be an area of a circle. We're going to combine both vectorized math functions and scalar arithmetic. So this is an exercise for us. Given our radii, we'll have to multiply them by pi. We can access pi via the NumPy library, np.pi, times, now the formula is pi times radius squared, times our array, which we have named radii, raised to the power of 2. And here we'll use scalar arithmetic. We're raising each element within our array to the power of 2. The formula to calculate the area of a circle, given the radius, is pi times radius squared. All of these radii converted to the area of a circle is 3.14, 12.5, and 28.2. So that was an exercise. mean, there's a mean function. Print the mean of our array. What's the average? The average value, 5.5. If you need the standard deviation, that is STD. It's the measure of spread within your data, 2.8. This is more of a statistics term, but just remember, in the future, you do have access to a standard deviation function. Or if you need the variance, that is VAR. VAR. 8.25. The variance is the square of the standard deviation. Again, it's more of a statistics thing. You may not use it anytime soon, but you do have access to it. If you need the minimum value, there's a min function. np.min, pass in your array. This will give you the minimum value, 1. Or there's max. np.max, pass in your array. 10. If you need the position of the minimum value, there's a function for that. It's arg, meaning argument, min. What is the position of the minimum value? This function will return the index number, 0. That's the first index. Or the max, that would be arg max. Then pass in your array. What is the index of the greatest value? That is 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, with your set of data, you can select an axis. For example, I would like to sum all columns. Here's how I would do that. With a lot of these functions, you can select an axis for them too. So let's print np, call the sum function, pass in our array. Then with the sum function, we can pass in a second argument. I will select an axis of 0. If axis is 0, we're applying this function to all the columns. So here's our new array. We're summing all of the columns. We have 7, 9, 11, 13, 15. If I set axis to be 1, we're going to sum all the rows instead. And we should have 2 values within our array, 15 and 40. 15 is the first row summed. 40 is the second row summed. All right, everybody, those are aggregate functions. They summarize data and typically return a single value. There are more functions than what we've discussed, but those are a few of the beginner-friendly ones. And well, everybody, that is an introduction to aggregate functions in NumPy. Hey everybody, in this video I'm going to explain filtering in NumPy. Filtering refers to the process of selecting elements from an array that match a given condition. We're basically filtering out elements that don't match a condition. Here's an example. Let's pretend that we have 2 classes of students, 2 groups. I'll put them within a 2D array for this example. Let's name this array ages to store the ages of our students. Ages equals MP dot array, and this will be a 2D array in this example. We'll have 2 rows. Make up some ages. 21, 17, 19, 20, 16, 30, 18. Then we got one person that's 65 that's going back to school. So let's pretend that this is a college class. Some students are still in high school, but they're taking college classes, and others are older and they're returning to school. Now for my second group of students, let's say one student is 39, that's Bob, 22, 15, one person's 99, 18, 19, 20, 21, that's good enough. By using filtering, we can filter out some of this data and create a new array. By taking our original set of data, we can filter out elements that don't match a certain condition, then use the elements that do match to create a new array. Let's say we'll create a new array of all the teenagers. Find anybody that's under 18. I'll create a new array. We'll name it teenagers equals, take our array, our original array, which we have named ages. Then here we'll write a condition. We'll create a new array where the elements match this condition. We'll say any ages that are less than 18. And then we can print it. Print our new array of teenagers. And it looks like we have three students under 18. 17, 16, 15. This is Boolean indexing. Now pay attention to the shape. By using Boolean indexing, this will flatten your 2D array. It's now one-dimensional. But there is a way to preserve the shape using the where function, but we'll get to that a little later in this video. This array of teenagers, it's a new array. By filtering out elements and creating a new array, we can preserve the original. We still have all the original students, the original ages of them. Alright, now let's filter out anybody that's between 18 and 65. We will say these are adults. Adults equals, take our original array, use the subscript operator, we'll write a condition. Return any ages that are greater than or equal to 18. Let's see what we have currently. We have a one-dimensional array, but we still have people that are 65 or older. We have 65 and 99. Here we'll need to use a logical operator. So let's enclose our first condition within a set of parentheses. Now with Python, to use the AND logical operator, you would write AND. But since NumPy uses C-style arrays, we have to use an ampersand. The ampersand is the C logical operator for AND. Now we'll match a second condition. Return any ages greater than or equal to 18, and any ages that are less than 65. Then let's take a look. We should have nobody that's under 18. We have two 18s, and nobody 65 or above. Doesn't look like there are any. Now you could use OR, which is a straight vertical bar, but we would have to change these conditions. So we'll say, if any ages are less than 18, or any ages are greater than or equal to 65, we would end up with an array of anybody below 18 or 65 or greater. So let's change that back. For seniors, perhaps they get a senior discount. Seniors, take our original array, use the subscript operator, check all the elements within our array of ages. Is their age greater than or equal to 65? And we should have 2. Let's print our new array of seniors. We have 2 students 65 or above. Someone is 65 and another is 99. Let's find any ages that are even. I'll name this array even, or evens. Take our array of ages, return any ages, use the modulus operator that gives you the remainder of any division. Modulus 2. If we divide one of these values by 2, if it's equal to 0, the remainder that is, put it within a new array of evens. Now we'll be given an array where all of the ages are even. 20, 16, 30, 18, 22, 18, 20. Or we can do odds. I'll name this new array odds. Ages modulus 2 does not equal 0. And then we'll print it, our new array of odds. We're now given an array where all of the elements are odd, not even. When filtering and creating a new array, if you need to preserve the original shape, there's a different function, the where function. Here's how it works. Let's create a new array of adults. Equals access NumPy, call the where function. We'll select anybody that's 18 or older, including seniors too. There's 3 arguments. The first is the condition. Return any elements within our array of ages that are greater than or equal to 18. Now the second argument is our array. And the third is a fill value. We want to preserve the original shape. If we're filtering out any elements that don't match the condition, we have some students that are under 18. We'll need to replace these values with something else. Let's put 0. Some people use -1. Some people also use NP, not a number, but we'll just stick with 0 to keep it simple. And then we will print our new array of adults. And it should retain the original shape. We have a 2D array, 2 rows, and let's see how many columns. 1, 2, 3, 4, 5, 6, 7, 8. It's a 2x8 shape. Any elements that don't match the condition are replaced with our fill value, which we set to be 0. But if I set this to be -1, well then, the fill value is -1. But we'll keep that as 0. The where function will keep the original shape of your array, but it's a lot slower than using Boolean indexing, which we have just discussed previously. I would only use the where clause if you need to preserve the original shape of your data, in this case, a 2x8. Otherwise, Boolean indexing will flatten your data when creating a new array. Alright everybody, that is filtering. It refers to the process of selecting elements from an array that match. Let's do this. To start working with Matplotlib, we have to be sure that we have the library installed. One easy way to check that, at the top of your IDE, if you were to import Matplotlib, if it's underlined red, you can hover your cursor over it and install the package by clicking this link. Now, if this pop-up doesn't appear, if you're using PyCharm, you can open up a terminal, Alt F12 is the shortcut, then use pip to install Matplotlib. Pip install Matplotlib. Enter. Give it a moment to install, and that's all you gotta do. We can close out of this terminal. And that red underline should go away. To check the current version, within a print statement, we will print access the library of Matplotlib dot dunder, meaning double underscore, version. Dunder again. The current version of Matplotlib that I'm using is 3.10.6. We can delete this print statement. There's a module called pyplot. It's found within the library of Matplotlib. It provides a user-friendly interface for plotting. We're going to import that module by following matplotlib with .pyplot. So altogether, import matplotlib.pyplot. That's a tongue twister. Just so we don't have to type this long name every time, we're going to give it an alias or nickname as PLT for short. So in order to access, here we go, matplotlib.pyplot, we're just going to give it a nickname of PLT. Here's how we can create a basic plot. We'll need a set of x and y coordinates. We'll start with a basic Python list for the x coordinates. We'll say x equals a Python list. Here you can type in some numbers. I'm going to type in some years. 2023, 2024, 2025, and 2026. And then for the y coordinates, this will be a separate Python list. Make up some numbers. In this scenario, let's pretend that we have different class sizes each year. Starting with 2023, there's a class size of 15 students. Then for 2024, we have 25 students, then 30, and 20. Feel free to pick different numbers if you would like. We have a list of x coordinates and a list of y coordinates. Each set of these elements is a pair of x and y coordinates. We have to be sure that they match. Now, to create a basic plot, we're going to access plt dot call the plot function, and then pass in our coordinates, x, y. The first argument is for the points on the x-axis. The second argument is for the coordinates on the y-axis. Now, if I were to run this, nothing displays. You also need to call the show function of your plot. Here's how. When we would like to show our plot, we will access plt, call the show function, in order to show our plot. Now, I'm using PyCharm. My plot appears on the right-hand side in a separate window, called Plots. Here's my x-axis with all of my years, but we'll have to do some customization in a future topic. Then here are all the y coordinates. For 2023, we have 15. 2024 is 25. 2025 is 30. And 2026 is 20. And you can change these coordinates too. I don't know, I'll set 30 to instead be 1,000. Let's see what this looks like. And we get a different plot. But I'll change that back. You can also close out of past versions of plots by hitting this X button next to each. Now for the plot function, if you only pass on a single parameter, this argument would be for points on the y-axis. And here's what that would look like. The default behavior for plot is to start at 0 and place a point at each increment of 1. 1, 2, 3. But each of these ticks, they increment by 0.5 each. The points on the x-axis will be provided to you. But we'll pass in both x and y. Now, if you're familiar with NumPy, we could instead use NumPy arrays because they're faster than Python lists. To set that up, we will import NumPy as NP for short. We'll assign x to be a NumPy array, np.array function, and then pass in your Python list. Then do the same thing with y, np.array, pass in your Python list. And that's all you have to do. NumPy arrays are faster than Python lists, and give you more functionality. Your homework is in the comments section. Either post 2 lists or 2 NumPy arrays. Try and think of something creative if you can. Alright everybody, and that is an introduction to creating basic And here's what we got. Our line color is now a very specific shade.
Meet Boreum, your AI-powered research companion.
Now, let's say we have more than one line to customize. I'm going to create another NumPy array. We'll rename y as y1, plot x and y1, then we will also have y2. And I'll just do some copying and pasting. y2 will have some different values. Make up some values. I'll say, I don't know, 17, 23, 38, and I don't know, 5. Again, your values don't have to be the same as mine. Feel free to pick some different numbers. We're plotting x and y1, but we'll also plot x and y2, that set of coordinates. Access PLT, call the plot function, pass in x and y2. So now we have two lines, but our second line doesn't have the same customizations as our first line. Here's one option, although I don't recommend it. You could copy and paste all of these keyword arguments and pass them in. This would work, although here's a much better option. You could instead create a dictionary with all of these keyword arguments. And then when we plot a line, we can just unpack our dictionary. Here's how we can do that. Let's create a dictionary which we'll name line_style. This will equal call the dictionary function to create a dictionary. We'll cut all of these keyword arguments and then place them within this dictionary function. Now we could just pass in this dictionary when we plot a line. We just have to unpack it using double asterisks. Unpack the line style dictionary. Then it's as if we're passing in all of these individual keyword arguments. We'll do this for the second line as well. Unpack our line style dictionary. And it's the same. Let's create a third line. We'll name this line y3. This will be another NumPy array. Make up some values. 13, then 15, 20, and 30. Then we'll have to plot this line. Access PLT, call the plot function, pass in our new coordinates, x and y3. Then we will unpack our dictionary of line style. Then we should have a third line, which we do. All of these lines are the same color. That's because with our dictionary of line style, we've set all the colors to be the same. But you could pass in an individual color. Think of this as the default color for all lines if we use the line style dictionary. Another option is that we can cut this keyword attribute of color and then pass that as a separate keyword argument as well as the line style dictionary after unpacking it. So let's pass in a color, then pick a color. I'll keep the first line to be blue. We'll pass in a different color for the second line. Then for the third line, I'll pass in a color that's red. That's good. And now each of our lines has a different color. Alright everybody, so that is some basic plot customization. In the next video, we'll discuss labels. To help increase engagement with this video, comment down below what your favorite food is. And well everybody, that is an introduction to plot customization using Matplotlib. Alright everybody, in this next section, we're going to customize various labels, our title, and the ticks of our chart. Here's how we can customize those. In this demonstration, I have various class sizes year by year, the years 2023 through 2026. These are all NumPy arrays, but you can use Python lists too. To set a title, we're going to access PLT, call the title function, and then we can pass in a title as a string. We'll set the title to be class size. Then we will run this and we should have a title. Class size, although it's kind of small and hard to read. Here's how we can customize it further. We can pass in some keyword arguments. one of which is font size, to change the font size. I'll set that to be 20. Here's the new title. You can also change the font family, and it's just family. I'll pick Arial. That's a professional looking font. You can set the font weight to be bold. Font weight equals the word bold. Let me make the title a little bit bigger. Let's say 25. That's better. Let's also set a color for our title. Color equals, here you can pick the name of a color. You can use RGB values. You can use hexadecimal values. I'll pick something kind of dark blue, like that. I'll copy the hex value, and then set the keyword argument of color to be that hexadecimal value. And now our title should be a specific shade of blue. Now we'll set a label for the x-axis. We will access PLT, call the function of x label. We'll set the label to be year. And we should have a label on the x-axis for year, although it's kind of small. We'll change the font size. We'll copy the font size from our title, but set it to be 20. Here's the new font size. Let's change the font family. I'll pick Arial again. I'll set the font weight to be bold. And then I'll pick a color. I'll pick a lighter shade of blue. Let's try that. Color equals that specific shade of blue. Yeah, not bad. The label is kind of close to the border. We'll be adjusting the margin a little bit later in this topic. To create the label on the y-axis, I'm just going to copy everything within this x label function, paste it, change x to y. We'll say the text will be, let's change the text of the label to be students, as in number of students. We should have a similar label on the y-axis. Now we're going to customize the ticks of our graph. Each of these ticks is incrementing by 0.5 each. You can kind of see that here. You can force ticks to only display at these values for the x-axis. Here's how. We'll access PLT, call the x ticks function, x ticks, then pass in our list or NumPy array that we're using for the x-axis. So now we have ticks only at each given year. 2023, 2024, 2025, 2026. Now to customize the ticks, we will access PLT, call the tick params function, meaning tick parameters. To select an axis, you'll select the keyword argument of axis. You can select X, you can select Y, or you can select both. We'll select both. We're going to select colors, plural, not singular. I'll select the same color as my labels. Now the ticks should be blue. Alright everybody, so that is how to add various labels to your plots in Matplotlib. On the x-axis, we'll have 1, 2, 3, 4, 5. On the y-axis, we'll have 5, 10, 15, 20, 25. It really doesn't matter. We're more focused on the grid lines today. We'll need a plot, access PLT, call the plot function, pass in X, pass in Y. Then access plot, call the show function to show our plot. Here's our sample plot. Now let's say you would like to create some grid lines. For better readability, here's how. We're going to access PLT, call the grid function. Let's see what happens if we don't pass in any arguments. These are the grid lines with no customization. We have grid lines on the x-axis and the y-axis. If you would just like a single axis, you can specify that with the keyword argument. Axis equals, we'll pick the x-axis to begin with. We will only have vertical lines then on the x-axis by setting the axis to x. If we were to set this to y, we would have grid lines on the y-axis. You can change the line width. Line width equals, normally it's 1, but here's 2. The lines are a little bit thicker. Here's 3. Let's set that back to 2. You can change the color. Color equals, then select a color. I'll just pick light gray to keep it simple. The lines are now light gray. You can specify a line style. Normally it's solid. Let's try dashed. Here's dashed. Here's dotted. Here's dash dot. But let's set this back to dashed. Alright everybody, that is a super quick lesson on how to chart. A bar chart compares categories of data by representing each category with a bar. Here's an example that I thought of. You know the food pyramid? We'll create a bar chart to represent daily consumption of categories of foods. Here are the different categories. This will be a Python list. Categories equals, we'll create a Python list. The first element within this list will be grains, such as bread. Then fruit, vegetables, protein, dairy, and sweets. We'll create another Python list of values. For each of these categories, what value should each of them have? Let's pretend that these values are for daily servings. How many in each category did I consume today? We'll make up some numbers. For grains, this will be 4. Fruit, 3. Vegetables, I don't eat very many vegetables, that will be 2. Lots of protein, that's 5. Dairy, 3. And sweets, 1. But feel free to make up your own numbers. Now, although it's not necessary, I'm going to convert these Python lists to be NumPy arrays. Alright, we are ready to make a bar chart. Categories will be on the x-axis, values will be on the y-axis. Rather than using a plot, such as plt, called the plot function, we're instead going to use bar to make a bar chart. First, pass in what's going to be used for the x-axis, categories, comma, then the y-axis of values. And then you do have to show your bar chart. plt, call the show function. And let's see what we have. Here we go. A bar chart compares categories of data by representing each category with a bar. Here are the categories that we've stated. Grains, fruit, vegetables, protein, dairy, sweets. And here are the values on the left-hand side for each. Let's add a title and 2 labels to our bar chart. plt, called the title function. Then pass in a title as a string. We'll say daily consumption. Let's make sure that works. Yes, it does. We'll add a label to the x-axis. plt, x label. We'll say the word food. Yep, it says food. And you can change the size if you want for these labels, but that might be overkill for this lesson. We've already covered that in the previous topic. plt, call the ylabel function. We'll pass in a string that says quantity. And it should say that on the left-hand side. Now let's change the color of our bar chart. When we call the bar function, we can set the color to be a color of your choice. You can pick a color name, you can use hexadecimal values. I'll just say sky blue. And the bar colors should change. Now, if you would like a horizontal bar chart, I'll comment this line of code out, copy it, paste it. You're going to instead call the bar h function for a horizontal bar chart, which looks a little something like this. But honestly, for me, I prefer the vertical bar chart. Alright everybody, so that is how to create a basic bar chart using Matplotlib. We are now going to create a bar chart using Matplotlib. A bar chart, it's a circular chart divided into slices to show percentages of the total. It's good for visualizing distribution among categories. In this demonstration, we're going to create a fictional college. There will be 4 classes: freshman, sophomore, junior, senior. We'll create a Python list of categories. We'll have freshmen, sophomores. I think I misspelled that. Juniors and seniors. We'll also create a Python list of the number of students in each class. Values equals a Python list. We'll have 300 freshmen in our college, 250 sophomores, 275 juniors, and 225 seniors. If you're familiar with NumPy, you do have the option to convert any numerical Python lists to NumPy arrays. Although for a list of 4 values, it's not really too beneficial. If this were a larger dataset, we would benefit from NumPy arrays more, but it would be a good habit for us to develop. Now, Python list of strings don't really benefit from NumPy arrays. We'll keep that as is. We have the 2 collections that we need, categories and values. To create a pie chart, we will access plt, call the pie function, pass in our values. Let me show you what just passing in values will look like. We will also call the show function, plt.show function. We do have the distributions, but we don't have any labels. Here's how to set the labels. When we call the pie function, we will pass in a few keyword arguments. The first will be labels. What are the labels of our pie chart? The labels will be the categories that we have. Labels equals categories. And we should have some categories for each of these pie slices. Freshmen, sophomores, juniors, seniors. You can add some percentages to each of these pie slices. Here's how. That's going to be another keyword argument. The keyword argument is auto PCT. This means auto percentage. We have to set this equal to a formatting instruction. We're going to use %1f. Let's see what we have. All right, we don't need all these digits after the decimal. Let's limit that. After 1, we'll add 0.1 to display 1 digit after the decimal. 28.6, 23.8, 26.2, 21.4. To add a percent sign after, we'll use double percent signs, because normally using 1% sign is a format specifier. Okay, now there's a percent sign after each of these numbers. Here's how to set the colors for each pie slice. We'll create another list for convenience, which I will name colors. Colors equals. Then in order of your categories, place a color within here. You can choose a color name, RGB values, hexadecimal values. We'll just keep it simple and pick some color names. Freshmen will be red. Sophomores will be yellow. Juniors will be blue. Seniors will be green. And then we do have to pass that in as a keyword argument. Set colors equal to our list of colors. And the colors should change. Freshmen are red, sophomores are yellow, juniors are blue, seniors are green. Let's add a title to our pie chart. PLT, call the title function, pass in a title. My college will be named Bro Code College, because I think I'm cool. You can explode one of these pie slices. Explode means to displace it slightly, if you need to highlight a pie slice. We'll explode seniors. For the keyword argument of explode, we'll set this equal to a Python list. We have 4 categories. We'll need 4 values. I'll set each of these to be 0. I need to explode seniors. I'll set this to a value that's not 1. Let's start with 0.1. The greater the number, the further the distance that PySlice will explode. Here's 0.1. Let's change that to 0.2. The distance traveled should be a little bit greater. Here's 0.3. We'll set that to be 0.2. That's pretty good. 0.1. We can also add a drop shadow. Shadow equals true. And there should be a drop shadow for each pie slice. To rotate your pie chart, you'll set start angle to be some angle. If I were to set this to be 180 for 180 degrees, my pie chart is going to rotate by 180 degrees. I'll just set that to be, let's check out 90. That's pretty good. To discuss scatter graphs in Matplotlib. Scatter graphs show the relationship between 2 variables. They help to identify a correlation, positive, negative, or no correlation. For example, the more hours you study, the higher your test scores tend to be. That's a positive correlation. Scatter graphs help us identify those correlations. In this demonstration, I'll create the following dataset. You can either follow along and type what I'm about to type, or look in the comment section. I'll try and post this dataset. We'll have X, which will be a Python list. These will be hours studied for various students. We'll have 10 values. The first student didn't study at all. They studied 0 hours. Another studied 1 hour. 1, 2, 3, 4, 5, 6, 7, 7, 8. Feel free to make up some numbers too. It really doesn't make a difference. Then Y will be the test scores. This will be another Python list. The student that didn't study at all, they got a 55% on their test score. The first value will be 55. Then another got 60, 65, 62, 68, 70, 75, 78, 82, 85, 87. That's good enough for now. To create a scatter graph, we're going to access PLT, call the scatter function, pass in X, then pass in Y. X is for the hours studied. Y is for the grades. What grade did they get on their test score? Then in order to show this graph, we have to call the show function, plt.showFunction. Let's see what we have. Here's our scatter graph. You can see that there's a positive correlation between hours studied and the exam scores. Let's add some labels to our scatter graph. For the X label, access PLT, call the XLabel function, then pass in a string to serve as the label. Hours studied is good. Let's make sure that that works. Yes, it does. We have a label for hours studied. For the Y-axis, call the YLabel function, then pass in a string. We'll say grades. Or grade, singular. Let's make sure that that works. Yes, it does. Here's the grade. Then let's add a title. PLT, call the title function. I'm going to say test scores, just as a general title for our scatter graph. Let's add a little bit of customization. Let's change the color. This will be a keyword argument. Color equals some color. You can pick a color name, you can use RGB values. I'll just say sky blue to keep it simple. And the color should change, which it does. You can also change the alpha. Alpha is related to the transparency. If I set alpha to be 0.5, that's 50%. The transparency is going to change, although it's a little hard to see. If I set alpha to be 0.1, then the transparency is 10% and you can barely see it. I'll keep it at 50%. Let's change the size of our dots on our scatter graph. That would be S for size. Let's check out 100. That's bigger. Here's 200. Yeah, we can keep it at 200. That's a good size. Okay, let's create another data set. The following set of scores will be for one class. We'll add another class of scores. Although it's not necessary, I forgot to make these NumPy arrays. You can if you would like. Let's rename X to be X1, Y to be Y1. Pass in X1 and Y1. We're going to create a whole nother set. Let's copy and paste X1 and Y1, rename them as X2 and Y2. And let's change some of these values around. For the second set, we'll have 0, 1, 2, 2, 3, 4, 5, 6, 7, 8, 8. Then for the exam scores for the second class, we'll have 50, 58, 65, 70, 72, 78, 83, 88, 92, 95, 97. We're going to call the scatter function again. We'll copy and paste what we had previously, but pass in X2 and Y2, the second set of coordinates. Let's change the color to be red. The blue set of dots is for class 1. The red set of dots is for class 2. Based on this graph, we can't tell without a legend. The legend will tell you which class is which. But we'll need some labels. We'll pass those in as keyword arguments. For class 1, we'll set label equal to class A. And then for our second class, this will be class B. Label equals class B. But then we have to show the legend, because it's not visible. Access PLT, call the legend function. Then we should have a legend within our scatter graph. Class A is the blue dots. Class B is the red dots. Alright everybody, so those are scatter graphs. They show relationships between two variables. For example, hours studied and exam grades. The more hours you study, the better grade you tend to get. That's a positive correlation, which we can see from this graph here. And well everybody, those are scatter graphs using Matplotlib. This video I'm going to explain histograms in Matplotlib. Histograms are a visual representation of the distribution of quantitative data. In short, we can visualize the distribution of data. Histograms group values into bins. Think of these like intervals. We'll count how many fall in each range, in each bucket or bin. Histograms are great for statistics and probability. In many cases, you'll see a bell curve distribution. Now, in this demonstration, I recommend using NumPy because we'll need a lot of data to work with. With NumPy, we can generate some random numbers. Here's how we can do that. We're going to create some test scores. We're a teacher and we have 100 students that each took a test. We'll create a visual to display the distribution of scores. We'll create a NumPy array of scores. Scores equals NP, axis random, then call the normal function for a normal distribution. There's a few keyword arguments here we'll pass in. The first is LOC. LOC equals, LOC is the location of the center, the median of our data. For the center, we'll say that the median is 80%. All of the test scores are going to cluster around this score of 80. Most students will do pretty well. If this were a lower score like 50, that means most of the students failed. That's because the most frequent score is going to be around 50%. We'll set that to be 80. Now we'll need a scale. This is another keyword argument. Scale equals, scale is the standard deviation, the spread. How far away are the scores going to deviate from the center? The higher the number, the greater the deviation. Let's start with 10. And then we need a size. How many numbers do we want to generate? We'll set size equal to 100. We have 100 test scores. Let's test what we have currently. We'll access PLT, call the hist function for a histogram, pass in our NumPy array of scores. Then we do have to call the show function to show our histogram. Axis PLT, call the show function. Here's what a histogram looks like. We set the center to be 80. Scores around that number are going to be the most frequent. And we've set the scale to be 10. 10 is the standard deviation. That's a statistics and probability term. How far away will the scores deviate from the center? Now, if I set the scale to be a small number like 1, the scores are going to cluster more closely to 80. The lowest score was 77, the highest score was 82. If I set scale to be a big number like 50, well then the scores really deviate from the center of 80. We have some students that scored below 0 and others above 200. Let's set that back to 10. Just to ensure that no scores go below 0 or above 100, we can use the clip function. We'll reassign our NumPy array of scores. Access NumPy, call the clip function. We have to pass in our NumPy array of scores. For any scores below 0, we'll set them to be 0. We'll clip them. For any scores above 100, we'll clip them down to 100. It's kind of like we're setting the bounds, the minimum and the maximum. All scores below 0 will be set to 0. All scores above 100 will be set to 100. Let's set the scale back to something massive like 50. Yep, there's no scores below 0 and no scores above 100. But we don't need a scale that big. Let's add some customization. You can set the number of bins that you want as another keyword argument. This will be within the hist function for a histogram. I'll set the number of bins to be 10. We should now have 10 bins, or intervals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I were to set this to 20, we would now have 20. But I think 10 is a good number. Let's change the color. That's another keyword argument. Color equals pick a color. I'll just set my histogram to be light green. There we go. To better define the edges, you can set an edge color, because right now it kind of looks like one massive blob. Edge color equals, I'll set it to be black. We should get a nice outline around each interval, or bin. Let's add some labels because, well, I forgot to do that. Let's add a title, PLT, called the title function. We'll say exam scores. Let's make sure that that works. Yes, it does. Let's set a label for the x-axis. PLT, call the xLabel function. We'll say score. Here we go, score. And for the y-axis, PLT, call the yLabel function. Number of students. Number of students is on the y-axis. Alright everybody, so that's a histogram. It's a visual representation of the distribution of quantitative data. We're displaying the distribution of data. And well everybody, those are histograms in Matplotlib. You can create subplots using Matplotlib. There's a couple definitions we'll need to cover, one of which is a figure. A figure is the entire canvas in which we add a plot to. Then we have an ax. An ax is also known as a subplot. It's a single plot within a figure. A figure can contain multiple axes, or subplots. We're going to call a subplots function. It's going to return a tuple that has a few things inside of it. Just to demonstrate, temporarily I'm going to print axis PLT, call the subplots function. Within the subplots function, we're going to determine the layout of our figure. How many rows and columns of subplots will be within our figure? For example, we could have a 2x2, 2 rows, 2 columns, or 2x3, 2 rows, 3 columns. or a 3 by 2. 3 rows, 2 columns. Let's stick with the 2 by 2 for now. I want to show you what this function returns exactly. It's a little complex, but we'll break it down. The subplots function, it will return a tuple. The tuple has 2 entities, a figure object, which is our canvas, and a 2-dimensional array of axes objects. When we call this function, we're going to unpack this tuple right away. Rather than use print, we're going to assign what's returned to us and unpack it. We'll create a figure object and an axes object. Figure and axes equals call the subplots function. Figure is our canvas. We won't actually be using it in this topic, but we're provided with it by the subplots function. We'll print this 2-dimensional list right away. Here's how. We'll plot each of these subplots, but we won't add any data quite yet, not until later. If I was to call the show function, we can see all the subplots that we have. Axis PLT, call the show function. We have 4 subplots, 2 rows, 2 columns. If this were a 1 by 2, 1 row, 2 columns, we have 2 subplots. Or a 2 by 1, which would be 2 rows, 1 column. A 3 by 3 would be 3 rows, 3 columns. We don't need that many subplots, but I think you get the idea. We'll have a 2 by 2, 2 rows, 2 columns. We'll fill each of these individual subplots in. Here's how. We'll start with the top left corner. Row 0, column 0. We'll access our 2D list of axes at row 0, column 0, and then plot it, calling the plot function. We will need some data. We'll keep it simple. We'll say x equals a NumPy array with a list that contains 1, 2, 3, 4, 5. We'll plot x, but to keep it simple, we'll just say y will be x times 2. Let's take a look. We've selected the subplot at row 0, column 0, so only this one is filled in with our data. Let's customize it. Let's set the color to be red with a keyword argument. The color is now red. And let's add a title. We need to select that specific subplot using a set of indices. Axes at row 0, column 0. Call the set title function, then pass it a title. We'll say x times 2 for the title. And there's the title for this specific subplot. Now we'll plot the top right subplot. We need to select that specific one. That would be row 0, column 1. We'll call the plot function, pass in x. We'll say x to the power of 2 for the y-axis. Select a color. I'll select blue. Then set the title. Axes at row 0, column 1. We will set the title to be x to the power of 2. The top right subplot should now be plotted. Alright, let's select the bottom left corner. That will have different indices. Axes at row 1, column 0. We'll call the plot function, pass in x. For y, we'll say x to the power of 3. We'll set the color to be green. Then set a title. Axes at indices of 1, 0. Call the set title function. This will be x to the power of 3. Oops, looks like I misspelled color. There we go. Some of these subplots are overlapping. You can add a tight layout so everything fits. Axis PLT, call the tight layout function, and now they should all fit in place. which they do. Let's finish this bottom right corner. I'll just copy and paste the last 2 lines. That would be axes at row 1, column 1. This will be x to the power of 4. The color will be purple. Axes at row 1, column 1. We'll set the title to be x to the power of 4. There we go. We have now filled in the bottom right corner. Now, if this were a 3 by 3, well then only these 4 subplots are still filled in, but we really don't need that many. Now, you don't necessarily need to use plots. You could use different graphs instead, such as a bar chart, or whatever else you would like. Alright everybody, and that is how to create subplots using Matplotlib.